Okay, good morning everyone. I hope you are all feeling well today. Well, my name is Aldo Reyes and I am the General Coordinator of Preserve. And I'm more than happy to see all of you today here. I would like to start saying thank you to all of you for your time and for the effort to come here to the event. All of you, partners and guests. And I hope you have a good day over the day today. Well, we are Preserve. Preserve stands for, as you can see, high performance sustainable bio-based packaging with tailored end of life and upcycled secondary use. You will see during the session what this means, what we have done in reference to that, and what we expect should be done in the future. Preserve is a funded project by the European Commission under the Horizon 2020 program. It started in the 1st of January of 2021, and I had the great pleasure to take over the coordination in April 2021. Since then, I have been surrounded by an amazing team of partners doing the job, and everything you will see today is thanks to their effort, a team effort. As I said, the project has been running for 4 years. We started 26 partners. Now we end with 23 partners, but again, all of them have done a great job. We have had 4 different project officers. We have had COVID-19 in between. And I mention this because, as all of you can imagine, a research and development project using so many hours of laboratory may have some impacts on that sense. Fortunately for us, we managed this impact. We were not too strongly delayed for the COVID, and we have come up to today with the results that you will see during the session. The mission of Preserve is, or pretends to be, to enhance bio-based packaging not only in terms of their properties, but also to manage their end of life. This has involved strategic testing of different materials, compounds, and results, as well as complex understanding of coatings, adhesive, and the interaction and properties of all of them in different supports. Also, our target is to provide the corresponding entities with our results, our vision, and our recommendations regarding primary materials used in the packaging sector. Thanks to this very ambitious roadmap, we humbly expect that Preserve innovations could be an enabler factor to help replacing more than 60% of all food packaging by 2030. I will not extend too much on this introduction because I would prefer you to enjoy the session and to see the results and the roadmap that we will have to show you during the day. Thank you all. Welcome to the session. Welcome also the people that is online connected today. We will have the agenda. I don't know if maybe you have it or it will appear over here in a minute. We will have different sessions during the day. First, we'll have a big session regarding Preserve results, in which we will talk about different technologies, different solutions that we have used and we have come up during the project. And then we will have a quick coffee break in which all the speakers and all the partners will be around. So if you have any question or comment, please address to them directly. Then we will have a session based on the innovation roadmap and what does the future hold for Preserve and the packaging industry. In there, we will have 3 sessions internally. One will be an introduction about the innovation roadmap. Then we will have a roundtable about it, and then we will have different partners and speakers talking about the pioneering sustainable packaging breakthroughs and the path ahead. Then we will have lunch. And at 2 o'clock, we'll come back for a new session regarding synergy in action and breakthroughs from our other Horizon 2020 partners. In here, we will have our two sister projects, UpPet and Uplift. They have shared this road with us. And then we'll have also two invited projects, BioRadar and Bio4Human. Finally, we will close the session, and then we will have a networking session from 3:30 to 5. I hope you enjoyed the day, and as I said, if any of you have any comments or questions during the session, please address directly to the speaker you want to talk. Welcome and enjoy the day. Yes, here. So we start them. Okay, so with no delay then, let's start with the first session of the day, which will be basically a summary of the key results we have achieved in Preserve. I will moderate the session and I will introduce every one of the speakers for this session. And we will start with Dr. Kristina Eißenberger from Albstadt-Sigmaringen University. She is our scientific and technical coordinator as well in Preserve, and she will be talking about the whey protein, a bio-based oxygen barrier. So, Kristina.
Good morning, also from my side. Thank you for taking the time to join us at our final event. As Aldo already mentioned, I'm Kristina Eißenberger. I had the great pleasure to be the scientific and technical coordinator of this project. And I want to show you the results on our whey protein layer. But before that, I would like to introduce myself. So I work at the Albstadt-Sigmaringen University, and to be more precise, at the Sustainable Packaging Institute. So Albstadt-Sigmaringen may not be familiar with too many of you. So it's in southern Germany between Stuttgart and the Lake of Constance, as you can see here. And it's a nice city with an historic center and a less historic Forschungsfabrik where we are located. So the Sustainable Packaging Institute is involved in teaching and research in thick thematic areas. And as you can imagine by the name, our focus is on sustainable packaging concepts. Because we are on a mission to competently and holistically support all players in the entire packaging industry along the entire value chain of the life science industry towards the way to a more sustainable circular bioeconomy. And we do this with our 6 thematic areas, starting with biogenic raw materials, process technology and process design, because of course, when you work with new biogenic raw materials, you need or may need more new processes and new process designs. In packaging, everything is about function, so we are of course also involved in functionalization. As well as smart packaging, which comprises active and intelligent packaging. So active intelligent would be, for instance, the use of CO2 scavengers, whereas intelligent packaging would be the use of freshness indicators, for instance. Our 5th field is preservation and packaging, so we do storage tests, but also explore more recent sterilization techniques, such as electron treatment. And the last field is then bioeconomy and sustainability, so this comprises concept development, life cycle assessments, as well as together with our experts in fields, consumer perception studies, which we also did in Preserve, for instance. We are funded mainly by public projects, and as you can see, there are numerous projects, but of course we're here today to talk about Preserve. Aldo already introduced you to Preserve, but I would like to explain this chart that you can also see here a bit more. So basically, these are our objectives, starting from new biopolymer synthesis to produce packaging, but of course, it wouldn't be Preserve if we didn't have anything special for the project. So we have this, I always called it our bioplastic upgrading and upcycling toolbox. And within this toolbox, we, for instance, have barrier coatings, adhesives, PHA coatings, electron beam treatment, enzymation, and we use these different tools in different combinations to produce packaging. And at the end of life, we also have various options that we explored depending on the material, of course. So one option was biodegradation or enzymatic recycling, or delamination. I think you will also hear today about it from our partners from Planet Bioplastics. And with this, we end up with recycled polymers that could then enter again our upgrading, upcycling toolbox to produce new packaging or textiles and composites. And I would like to focus here on the barrier coatings, on the protein barrier coatings. So in the project, we used whey protein. Why did we use whey protein? Because it accumulates in large amounts in the dairy industry. The annual production in Europe is between 50 and 60 million tons, and roughly half of it is discarded. So actually, we could consider it a non-food competitive resource. Also, it is known to have the potential to compete with commercially available EVOH as in terms of oxygen barrier, and also to act as a separation layer. So actually, here, this whey protein layer. So when you have different substrate films coated with this protein barrier, it looks like this: substrate 1, substrate B, and in between the whey protein layer, which can be degraded so that the substrates can be delaminated and then separated and fed back into the respective material cycle. And now I'd like to show you some results. So I will only present for lab scale and pilot scale. We did this together at ASU with our partners from IVV. And what you can see is that our coating actually reduced the oxygen transmission rate to roughly 15 to 25 cubic centimeters per square meter day and bar, which means that for PLA we have a factor of around about 20 in the reduction of OTR. Can you see here for lab scale and for pilot plant? For PET, it's a bit less. It's about 2.5 to 3.5 factor reduction. And for PE, because it has like a very, very high oxygen transmission rate, the reduction was even in the factor of 300 range. But then we thought, okay, can we reduce it any further? Is it possible to actually metallize this layer? Because ideally, metallization takes place in vacuum, which means you have to get rid of the water within the coating. So ideally, you would expect that you get some cracks and that it won't work. Surprisingly, it worked relatively well. We were very happy with that. So this is a metallized whey protein coated PET film. And as expected, the metallization led to a further reduction in the range of factor of 130 for PLA, around 100 for PET, so we are here now, and a little bit less for PE, only a factor of 6. And interestingly, when we look at commercially available metallized PLA films or PET films, our combinations of the substrate film with the protein layer and then subsequent metallization outcompetes the commercially available metallization layer. So, to sum it up, it was possible to actually apply this whey protein coating on pilot scale. We actually could show that we can reduce the OTR of the substrate films. Also, the metallization was completed successfully, which we are very proud of, that we actually managed to do that. Very proud of our partners at IVV. And also that the combination of our protein layer together with the metallization outcompetes metallized substrate films. But we still have some open challenges that we could not close. So one was lamination. We realized that in order to laminate whey protein coated substrates, there needs to be a good adhesion of the whey protein layer to the substrate. And depending on the substrate material, this was not always the case, like for PLA. I think there needs some further innovations to actually overcome this issue, but for other substrates like PET and PE, it actually worked very, very well. And one open point that will be answered in another talk today is on the upscaling. Can we upscale it to industrial level? But this will be answered in around about half an hour by my colleague or partner from Südpack by Guerra. So with this, I'm at the end of my presentation. I'd like to thank you for your attention. And if you have any questions, feel free to ask. And of course, I'd also like to thank all of our partners that were with us on this very, very challenging, bumpy, but always friendly atmospheric road. Thank you.
Thank you, Kristina. We will do a Q&A session after all the speakers have passed by here, so it will be probably easier. Okay, so now we go to a new generation of PHA-based food packaging by Willem from Centexbel.
Thank you. So, as introduced by Aldo, I will now give a presentation on results, both from myself at Centexbel and from colleagues at Aimplus and Graphic Packaging about a new generation of PHA-based food packaging. To start out, a quick mention about Centexbel, who we are and what we do. So Centexbel is a collective research and technical center for both the textiles and the plastics converting industry. We are located in Belgium, and we are specialized on the one hand in research and on the other hand in testing for textiles and plastics. To give an example, during Corona, all the mouth masks used in Belgium were certified by Centexbel. One of the research topics we work on a lot is bio-based materials, and one of the more interesting, of course, bio-based materials is PHA. For those not familiar with PHA, PHA is a short word for polyhydroxyalkanoates, which is a bacterial polymer. This material is produced by bacteria. If you give them too many carbohydrates and not enough nutrients, they will store these carbohydrates in their cells like small polymer granules, which you can then extract and use for future applications. If you extract them, you end up with something like this. So it's really small granules of about 1 micrometer in size that you can either use as such in coating formulations, or you can convert them into pellets and then use them in extrusion processes. We then used this PHA either as a powder or as a pellet for 3 different demonstrators, all of them targeted towards Danone. So the films were used in these kind of pouches. We made barrier layers that could be applied on paperboard for the Tetra packs that you might all know. And finally, we also looked at replacing typical yogurt cups that are currently made out of plastic with molded fiber that was coated or lined with a PHA barrier layer. So the first way we wanted to replace these materials is with a PHA film, so using the PHA film for the pouch or to line the molded fiber cup. The issue is that PHA is not an easy material to work with. So the first trials, as you can see, the material was quite sticky, the melting strength was too low, so really the first films, very difficult to make. They had some defects, but in the end, after quite a few optimizations, making blends of PHAs, combining them with additives, Aimplus got to a really nice and stable process where they are now able to make those PHA cast films. They then made them in different thicknesses. Initially, the target was to go quite thin to save on material, because of course that's also an interesting and important aspect of sustainable packaging, where they made them at about 35 microns with a water vapor transmission rate of 2.6, measured at 6 degrees. However, when converting the packaging, and this will be highlighted later on as well, there were some difficulties with these thin films. So for that reason, thicker films of 80 micron were produced as well. And with those, the different demonstrators could be prepared. So what you see here on the left is, for example, one of those pouches filled with the yogurt, and one of those molded fiber cups lined with a PHA film. The results are not perfect yet. There is still some work to do on the processing and on the adhesion towards the molded fiber cup. But considering where we started and the time frame, we got quite far already. Then one of the demonstrators, which was the pouch, also was tested towards the conservation of the food. And what we saw is that if we compare the preserved demonstrator with materials supplied by Danone, that over a certain time period that we see no color change or no pH change in the material with both types of packaging. Then the next aspect that I want to highlight is if we start from a PHA powder directly and try to apply it as such as a coating. This is work we did at Centexbel, and the way we did this is with a plastisol coating. Plastisol is quite well known in the textile industry from PVC, but in essence, it's a blend of a powder and a plasticizer. If you heat the blend, the polymer powder, in this case PHA, melts, absorbs the plasticizer, and once you cool down, you end up with a solid film that has quite a number of applications in packaging, but also in the textiles industry. So if you do this with PHA, you end up with something like this. It's a viscous liquid that can be applied on, for example, paper-based substrates. So this is what we did. We took this PHA plastisol, we applied it on paperboard, first on lab scale. Next, towards the end of the project, we also upscaled this towards a roll-to-roll scale, where you see that we got a relatively even coating. And then we measured, of course, also barrier properties. So we measured these materials at 6 degrees, at 23 degrees, and at 38 degrees. And since we're looking at mostly dairy products that are kept in the fridge, we focused on the 6 degrees, where we ended up with a water vapor transmission rate of about 2.7 grams per square meter per day. Then we converted the material into some kind of a brick, but because a brick is too complex for quite a research project, we ended up with a small pouch. The only issue there is that we still have some issues when we start to fold the material. So one fold usually is not a problem, but if we have a double fold right in the middle, we start to have a leak. So this is something we still have to fix in future developments. But in the end, we still ended up with a barrier layer that has quite promising properties already. Secondly, the plastisol, one aspect that I just showed is that we can coat it directly on paper. Of course, if we want to coat 3D objects, then we need to find a different technique. And this is why we also use this plastisol as some kind of a dip coating method to coat a 3D object, such as the molded fiber cups used for the yogurt cups. This was a development that only started later on, but still quite interesting properties. So, for example, if we measure how much water is absorbed in such a coated cup after 30 minutes, we see that only 0.03 grams of water is absorbed in 30 minutes through the coating, which is essentially nothing. It's a little bit of moisture on top of the surface. So quite interesting properties. However, this dip coating is something that is not really easily scalable. So at Centexbel, we're still looking into methods like spray coating or other methods to really upscale the processing of applying the coating on these 3D shapes. And with that, I would like to close just some take-home messages that, as you can see from the presentation, PHA is quite a promising material when it comes to packaging, both for flexible and for fiber-based substrates, but we still need some final fine-tuning and further developments towards sealability, adhesion, and some of the processability. If you have any questions, of course, you can ask them in the end, or later on contact me or the colleagues from Aimplus or Graphic Packaging. And with that, I would like to thank you all for your attention and pass on to the next speaker.
Thank you. Thank you, Willem. Also, I mentioned just that these presentations will be uploaded later on, so you all will have access to them. Now we pass Innovative Biotechnological Strategies for Recycling Biodegradable Materials by Stephen Verstichel from Normec.
Hello, good morning, everybody. And thank you, Aldo, for the introduction. As mentioned by Aldo, we will tell you more about some strategy to recycle biodegradable materials. First, like usual, a few words about our company, Normec OWS. We are located in Ghent, Belgium, just as in Centexbel, close in the beautiful city of Belgium. But we also have a lab in America, Dayton, Ohio. What we offer is mostly services on biodegradation, composting, and ecotoxicity. For this, we are recognized worldwide by all certification institutes, and we also are a member of different standardization committees like CEN, ISO, ICM. We strongly believe in standards to compare results. Apart from these biodegradation services, we do waste inspections. So we check the purity of kind of waste, which is important for selling these materials for recyclers. Also do we waste and litter analysis. In the next department, we offer sustainability assessments like LCA, carbon footprint, EPF, and EPD analysis. We have consultant services for training workshops and mainly on the issue of biodegradation. And we offer also assistance in certification. Now let's go back to preserve. We know there are several recycling strategies for packaging, for plastic packaging. The most used is the mechanical recycling, for which we need to sort the material. We know there are some issues because there's some quality reduction after each run. So we have to apply also virgin materials. And it's also the technology is often not suitable for laminates and blends. Another approach is the recycling by dissolution. So again, we need to have some pure streams. So we need to sort these materials. We apply solvents, which are sometimes not really environmentally friendly, add new additives to make a new product, and also less suitable for laminates and blends. The third one, which is now more and more performed for research, is chemical recycling, like depolarization, pyrolysis, and gasification. Again, we go to the pure streams, but this is really a circular approach. You can make new materials. You don't have to add normally virgin materials. That's the purpose. But also we know now that for these biodegradable materials, there are more options, also more biotechnological options. Two main differences. One is compostability, mainly on an industrial scale, if you call it organic recycling. And the other one is anaerobic digestion. In anaerobic digestion, there's no oxygen present, so we have the formation of biogas, which is an additional advantage. You can use it as electricity and to make heat. So these materials are especially suitable for food packaging application because you can treat the disposed food together with your packaging. Certainly, when there is an expiration date that has been exceeded, you don't have to separate it. You can directly put it in your composting fraction. It can be used for laminates and blends. Of course, all components must then be compostable. Also, there is already a transport and treatment system existing, so we don't have to find out something new to set up new plants. And this will increase even because it's also mentioned in the landfill directive that we need to separate our organic biodegradable waste more and more in Europe and that we send them to composting plants. When these materials are bio-based, like we want to develop in preserve, we have developed in preserve, we also have a circular approach, which is, of course, what we need. And a more new approach is the enzymatic recycling, which was developed in this project by Unibo, together with Aimplast that did upscaling. There we go with the enzymes back to monomers, and from these monomers we can make new products. Also, this is then a circular approach. You can really make a new product out of it. Now, we get some more in detail about organic recycling. So you see the two main recycling strategies. First is industrial composting. There's a well-harmonized EN standard existing. It's a EN 13432. And these set the requirements that need to be fulfilled for material that is to be industrial compostable. There are some requirements on the chemical characteristics. It may not include heavy metals. They have to have a high organic matter content. The next one are more on degradation. So you have to demonstrate that your material is biodegradable in industrial composting conditions, so at 58 degrees Celsius. You have to achieve 90% based on CO2 within 6 months. The other issue is also that your material doesn't degrade fast enough during composting process, so it should be disappeared completely after composting. There, the requirement is that you have to achieve 90% in 12 weeks, and there should be no issues with the compost quality. That is mainly also tested by ecotoxicity testing, so it's tested by plants, but in other standards also on worms. If your material, if your product fulfills these characteristics, you can have labels like the seeding logo of European Bioplastics, which has invited us, but there are also other logos existing. Like in America, they have the BPI logo for this. Another field is anaerobic digestion. Here, there's no oxygen present, so we have the advantage of the biogas production in this phase. Biogas from which you can make electricity or heat. And that is the benefit compared to industrial composting. But this process is more complex compared to the industrial composting. For this, no standard is yet existing. They are working on, there's not exactly a standard to treat these plastics or the packaging. And so there's also no certification yet possible. We have developed some ISO standards which we submitted, and we hope that there soon will be some more standardization on that. You can consider mesophilic anaerobic digestion plant in thermophilic conditions. Thermophilic is around 52 degrees that these plants are working. And you have systems which are wet, and you have systems that are more dry. Dry is then considered as a total solid content above 20%, so it's really not so dry. Here you can see that this can be a circular approach. This is also developed by European Bioplastics. This graph, you see that our compostable materials can go together with the green waste in our composting bin, get collected, can be treated, biogas in the case of anaerobic conditions, and compost in the case of the composting process. This compost can be used to have the plant growth, and so you can make new materials out of this. So it's a circular approach. Now let's get back to some results within Preserve. As you can see already mentioned by Kristina, we have developed a bio-based whey protein coating that had good oxygen barrier properties. And we also checked how these materials are degrading. So here you can see the results in compost at the 58 degrees, according to the ISO 14855. And here are under anaerobic conditions. So it's here is the green line, and here is the orange line. You can see that these waste proteins are really degrading very well. They are also degrading as fast as our reference materials, which was cellulose. Moreover, these products are also degradable under freshwater and marine conditions, not shown here, but we proved it in the project. So in the case of filtering, these materials will also degrade there. So that's a really big advantage for these products. Then we checked also if these materials will doesn't degrade fast enough in an industrial composting plant. So we have the PLA coated with the whey proteins on both sides, so 2.5 micrometers thickness. And we observed that after 1 week, this film was already almost completely disappeared. Only at the borders we saw some material. So it's a material that is indecomposable, and we proved that we can work with these bio-based whey protein coatings for such applications. Another one is a pH-coated paperboard. Was also these products were developed also by Centexbel. So we know that PHA is already biodegrading quite well. Also for paperboard, if you go for industrial composting, you don't need to demonstrate biodegradation because it's made of natural product, cellulose fibers or wood fibers. So it's in C, biodegradable under composting conditions. And we checked there the disintegration of this paperboard with the thickness of 51 millimeter and a grammage of 360 under these industrial composting conditions, which is typically 12 weeks, and in home composting. And we can see that these pH-coated paperboards worked really fine. So after 8 weeks, most was gone. 10 weeks, materials is disappeared. And also in the home composting conditions, it goes even faster. Paper, we know that it needs to fungi, which are more active at lower temperatures. So that's why you can have better results and a faster result under home composting conditions, which is typically performed at 28 degrees. So we have a product that is also compostable even under home composting conditions. We are now at the end of the project, but we have received recently quite a lot of materials, quite a lot of demonstrators to test. Some interim results you can see here. Also, we have developed a coated PLA tray. This was coated with PVH and PVOH and lacquer. You can see that this tray already disappeared after 4 weeks, so that's also material that has the potential to be industrial compostable. And the same for the pH-coated paperboard, was also shown by Willem from Centexbel. This is now running. It's 2 weeks. The current results, we see some signs of disintegration, and we hope that with the current thickness and the application applied, we can achieve complete disintegration within 12 weeks. So this is not the final results yet. We are still working on that. Another approach we followed is the one on enzymatic recycling. This was done, the work done by Unibo. We did a huge job there. They focused on PLA. And we all know that packaging of plastic is consisting of, has a high molar mass and consisting of polymers. These polymers we try to degrade enzymatically. This is a catalytic process to obtain oligomers or monomers. And with these monomers, you can use again to make the new product again. So you have a really nice circular approach. And this was the idea to recycle also our materials back again. So it's all simple on a graph, but in reality, it was much more complex. Unibo did a lot of work on the selection of the suitable enzymes. Enzymes, they work a little bit as a Kelox system, so the substrate must really fit to the enzymes to degrade the material well. And there's also a lot of process development needed to separate also the oligomers and monomers from the mixtures. But all this work was quite successful at the end, and Aimless was responsible for the scale-up then of this process. They've developed this process, and they showed that within 48 hours that we could achieve an 83% monomerization of this PLA. So this is quite a good result. So within 2 days, you can really monomerize your material and use these monomers back again to make new products out of it. They achieved a maximum rate of 95%, which was after a longer duration. So this was a really nice result of the project, and this is something that we will be further investigated and can be used then later on to recycle PLA. And this we came to the end of the project, so I thank the partners for their work together. And if there are questions, you can ask them later.
Thank you, Steven. Also, just to remind the people connected online that they can place their questions at the chat of the session, and then we will read them here live. Okay, so now Nicolò Fortunati from Planet will talk about material separation and recycling of multilayer films for packaging applications.
Good morning, everyone. My name is Nicolò Fortunati, and I'm a research and developer engineer who following the Preserve project for Planet. And I present the material separation and recycling for multi-material film for packaging application. And before starting, I would like to make a small introduction to Planet Bioplastics and Romero Plastic company. Planet is an innovative startup spin-off of the University of Pisa, born in July 2017. The company was founded with the aim of developing biopolymer compound for packaging and technical application. And the principal idea is to meet the customer requirement, shortening the distance between the academic research and the small medium size company. The other company is Romero Plastic, founded in 1983 as a family business. And for the beginning, the company specialized in the recycling plastic processing waste by transforming polymers such as PET, PP, PS, and PVC into recycling raw material. Romero and Planet in the Preserve project has two tasks. The first is to optimize the condition of the lamination process by removing the whey protein coating, which will lead the separation of different layers for multi-layer material and make it recycling more efficient and sustainable. And the second task is to set up a pilot plant in which the lamination process of different materials developed in the project can be take place. And in the first part of the work, I need a screening of different commercial soap and substance, such as saline, enzymatic soap, and alkali solution, was carried out to assess which are the most effective in removing the whey protein, in order to select the best combination of solvent and process condition. After this, the process was scaled up in order to identify and develop the optimal process condition. In this phase, the optimal solution ratio was assessed, and how often solution could be used in such a way as to minimize the use of water and soap. And the images show the material of multi-layer film of one of the preserve demonstrator before and after the washing process. And we can see how the metallization and the various film layer has been separated, making the material ready to be recycled and reused in new application, thus reducing the impact and the environmental impact of the packaging. The second task concerns the design and the construction of the pilot plant, where the delamination of the developed material takes place, and the process is divided in 4 blocks: the pretreatment, the delamination, the separation, and drying and pelletization. The pretreatment is necessary to make the material processable and transportable, including the grinding and the pre-washing of the material. The first process must undergo is grinding, and this makes the material easy to handle and increase the contact surface with the material and the washing solution. And once ground, the material was washed to remove wanted residues, which the material has previously go in contact. After this, the material is going the lamination step, and in this block, the material is delaminated to separate the single layer of the material. And after the material going in the separation, that involved in the separation of the material from the washing solution, and if the multilayer are made of polymer with different density, such as PA, PAT, is possible to separate them using a float sink separation. And after this, the material was drying and pelletized. The drying is necessary to remove the water after the washing, the remaining in the material. After this is the material is recycled in a extruder to obtain the pellets. Now I want to show a small video in which we see the use of the pilot plant for the material separation. So what we can achieve by the preserve project, protein coating can be removed from the protein films. Polymer film can be separated using the developed process, and metallization applied for the film can be easily separated. And possible changes that can be addressed are the spinning up the delamination process and scaling up in the process into industrial level. And the last is the contact information. We are fully available for any clarification question, and thanks for your attention.
Thank you, Nicolò. Now, Ana Guerra from Südpack will talk about upscaling bio-based solutions and its challenges.
So, good morning, everyone, also from my side. My name is Ana Guerra, and I work for the R&D department at Südpack company. First, I would like to briefly introduce Südpack as a company. We have over 1,000 experts and more than 10 production locations just focused on manufacture high-performance films. We work mainly in 3 areas: medical industry, food industry, and technical applications. The mission of this family-owned company is healthy planet, healthy people, healthy growth. Said that, I will go for Preserve project. As my colleagues already talked about, the main target of Preserve is to demonstrate that we can actually substitute fossil-based packaging with innovative and smart bio-based solutions. Also, given some advice, how can we go for alternative end lives, like here in this schema. Sorry for that. So, how to achieve this? We wanted to have a broad spectrum of packaging solutions to demonstrate this. Therefore, we have for the food application 5 target packaging: a peel solution, a flow pack, a dairy pouch, a beverage brick, and a molded pulp. Here are the fossil-based solutions, and here you can see the advice that we work with in Preserve. How can we overcome the fossil-based material with innovative bio-based solutions? For this target, we need the help of some end users, in this case, Danone and Ferrero, and they support us, giving us which requirements are needed and how can we introduce this solution to the market. First, it's important to understand that the final packaging needs several production steps. First, we went for the production of many substrates, all of them bio-based, and we produce these materials, these films, with extrusion technique. Some of them with blow extrusion molding, and some of them with cast film production. As you can see here, we produce successfully at TRLs between 6 and 7 PLA films, self-reinforced PLAs. As I said, for bio-based solution, we have to be innovative, to be smart. How can we overcome the mechanical properties that sometimes are not comparable with fossil-based, and that's why we work with self-reinforcement here. Also, we successfully produce 30,000 meters of bio-based polyethylene film. As well, we work, as my colleague Willem already said, PHA is a really innovative bio-based polymer, which is not easy to work with, but we successfully produce 30,000 meters of a blend, and pure PHA is also a really important achievement to have, and we produce successfully more than 1,000 meters. Another important thing to say here is for a laminated structure, we have to overcome, not just to manage to do the substrate, we have to prepare coatings, we have to prepare adhesives, and that's why we also try to upscale the whey protein coating. as my colleague Kristina already said, in pilot scale work perfectly, but we have to point out that these coatings must be done on site. We have to do it on the production line where you are printing, because the shelf life of these coatings are very short. With the conventional machinery that we have at conventional converters, it's really difficult to achieve this, because you have to overcome the foam formation, you have to work with really low speeds and control temperature. We came out to the conclusion that some investments must be done, but we are confident these solutions are very sustainable, and still we achieved to do some semi-upscaling of a semi-industrial printing pilot line, producing around 36 kilograms of this coating. Now I would like to go to the process, how we achieve to do these packagings. First, we demonstrate the Ferrero Pocket to Go. That was a peel solution where we first work with a substrate PLA base, met PLA with whey protein coating and PLA. As my colleague Kristina already explained, we faced some troubles with the substrate and the protein coating. We saw that the adhesion force between layers was insufficient. But later on, I will explain that with other substrates, we actually successfully did the lamination. Therefore, we discarded this solution and we went for a mono solution with a coating. The same problem was faced for the tray. We saw that the lamination wasn't possible because the adhesion between layers with PLA wasn't successful. And now, if we want to make a change, we have to think in another way. And that's why we decided to go for another solution. This self-reinforced PLA had actually very good mechanical properties, and we thought, what about to increase the oxygen transmission rate just with a coating, PVOH in this case, and then we protect the coating with a lacquer. Afterwards, we successfully did this, and as you can see here, we produced the packaging with thermoform, and after thermoforming, we actually reach good final barrier properties. Also, my colleague Steven already told you that this packaging is biodegradable and was tested successfully. Again, depending on the substrate, we have better results. Here, we work for a flow pack, and then we laminate successfully PET metallized with whey protein coating and bio-based PE. The printing and lamination trials were really good, and we produced successfully 2,500 meters of this material. The final barrier properties are also very good, as you can see here, and we managed to pack the cookies on this packaging. I will go briefly here for the PHA solutions, because Willem already explained in detail what we did, but I would like to point out what were the challenges that we faced with the upscaling. First, as Willem already said, we have a very thin films of PHA, and when we put it in the machine, we saw that the mechanical stress under high temperature for this material was too high. Then you see we have some deformations. Also, we tried a solution with lamination, but we saw the same problem as with the pure PLA solution. We have difficulties with the adhesion between layers. Therefore, we rethink the solution and say, what about making a PHA, but a little bit thicker, and overcome these problems? And we successfully did this and produce mono PHA and make some pouches, as you can see here, with promising shelf life test results. For the beverage brick, also, we work with plastisols coating, and the upscaling reached the TRL 6 and was applied in paperboard. For the molded pulp solution, as already mentioned, we have two techniques. One was to try to use this coating, but with a new technique for doing it in 3D solutions. This could be done by spray coating, but this is still on definition. Because of time limitation, we couldn't finish this target path. Also, we also work with lining solutions, where you can see here, we lined some cups with monofilm of PHA. I have to be clear about this. work with PHA is not easy, but the know-how is there, and we work really hard to manage to line these cups. And as you can see, the final barrier properties are promising. We still have some small issues to overcome, like the narrow temperature window, some wrinkles, and so on, but we think that those are the foundations stones to go for an actually market-ready solution here. So, everyone is talking about recycling by design, but what are we going to do with these materials? This is something that we have to think about as well, and therefore, in Preserve, we wanted to have an upcycling option. That's why the food packaging solutions were rethink how can we use the recyclable material of these food packaging solutions on another application, in this case, non-food applications. Coming from the Hanuta packaging, we developed 3 possible packaging, also a flow pack, an injected jar, and bottles. And coming from PLA stream, we develop carrier bags and carrier boxes. Again, in Preserve, we are trying to work with bio-based solutions and substitute current fossil-based solutions. Here, as well, we work with the support of end users that help us to define how should we proceed, which are the requirements, and so on. For these solutions, it's the same story. We have different production steps that we have to go through to finally make a packaging. Therefore, first, we have to make compounds for the bottles as well as for the jars, and we successfully use recycled bio-based polyethylene and recycling polyester. Do some additivation, of course, that is always need to have a successful material, and we produce around 30 kilograms of these compounds. From the PLA stream, we also work with multifilaments and successfully produce 50 kilograms of these multifilaments. The challenge was here that the low melt strength of PLA must be overcome to have a stable production, and therefore some additivation was done, but still didn't affect the biodegradability of these materials. Another thing that we also spoke about is what happened with the microfiber release. When we wash our clothes, we have in many of our clothes some microfiber release. Therefore, we wanted to guarantee that we have a final solution that is actually sustainable for the environment. And therefore, we work with a finish coating for nonwovens where we were confident that we will reduce the microfiber release as well. This was a PLA solvent-based formulation, and we successfully produced between 5 and 2 kilograms in TRL around 5 and 6. First, we thought to use a roll-to-roll coating at higher scale, but we saw some difficulties to use this coating matching with this technique, but it doesn't mean that this coating cannot be used with another technique. Then again, if we want to make a change, we have to rethink things. Therefore, we went for another solution. What about we use this coating, but we spray? And we successfully done the production of this coating application on these nonwovens made by recyclable PLA. So, just again, going through the specific demonstrators. In the previous slide, we have like basis material that we need for doing the final demonstrators. But here, we are going to speak about the specific packaging that we have been done. First, the injected jar is based on this recycled PE and recycled PET coming from the compounds. We faced some challenge during processing by the upscaling. You can see thin walls here on the picture, but it's important to realize that the mold itself had some issues also with fossil conventional materials. Therefore, the advice here would be just to make some small changes in the mold. Unfortunately, we don't have the time to finish this, but here we doesn't see any big issue, and we are confident that with some more time we could make some adjustment on the mold and we could successfully done these jars. With the bottles, we also reached a pilot scale to produce 200 bottles. You can see some samples there. And then when we were from the upscaling, some small difficulties were faced. But again, the experts on this area were confident that with some adjustment, maybe because the main problem here was that the material was sticking a little bit on the mold, but with some additivation for helping the material to go not go stick with the mold would be overcome. The other demonstrator that we were with was the carrier bag. And here, this material that was coated with spray coating. Afterwards, we just produced with these non-wovens, coated non-wovens, coming from recycled PLA. We have to keep in mind that all these demonstrators are coming from streaming of recycling. And here you can see we finalized a bag without trouble. There you have also an example of it. Last but not least, we also work with these non-wovens and combined them with some fibers from Demet-X. And then we achieved to do, as you can see here, a mix of these materials. These non-wovens are here. And after going for thermoforming, we achieved to have these displays that you can use just for organizing your closet. Also a very nice application and innovative. So I come to an end to my presentation. I have to say thank you for everyone that was working very hard here. This is just 10 minutes, but we worked the last 4 years actively with innovative solutions, and I am very proud to the results that we have overcome today. Here, my contact information as well as my colleagues, and thank you so much.
Thank you, Anna. And we go to our last talk in this session. It's going to be shared between Carla and Matteo from ITENE and NTT. And it's about sustainability and circularity of bio-based packaging, the conclusions. So which of you starts? I hope you have already realized that we have some of the demonstrators on that side of the room. Please have a look at them, but don't take them home.
Okay. It's easy. Next, back. Okay. Okay. So, good morning to everyone. So I will talk about the sustainability aspect that we studied in this project. The philosophy at the base of our work is the sustainable development. That probably, as you know, is a development that meets the needs of the present without compromising the ability of future generations to meet their own needs. This one, the pyramid, is probably one of the most accurate representation of the sustainability because it explains the connection and the relative importance between the three sections that are environment, society, and economy. So, based on the sustainable development was the theoretical approach that we use, that is the life cycle thinking, that, as you can see, that emphasize the assessment and minimize environmental impacts at all stages of the product's life of a product of a process. So there are three parts in the sustainable development, And for each aspect, there is a methodology to try to study and to understand the impact of a product or a process. So for the economy, there is the LCC, for the society, the social LCA, and for the environment, the LCA, the life cycle assessment. So here, there are brief explanation of the three methodology. So life cycle assessment is the most standardized one because there are two important ISO rules, that is 14040 and 14044, that explain how to carry out an LCA evaluation. So we studied for the benchmark product and also for the preserve one. We carry out an assessment of all the material and energy that are involved in the production process for all these products in order to assess all the impact regarding the environmental part with the LCA. With the LCC, we try to evaluate the cost during the life cycle of the product. And with the social LCA, we try to evaluate the social impact and also the potential impact of this product. Next. Okay, how we work? We started to the study of the process because NTT is not a technical partner in this matter. So we work together, the technical partner of the project. We started to carry out and to define the flowchart of the process in order to understand how the process is organized and which are the input and output of all process. Then we started with the data collection. So we have a very long exchange of information between entity and the technical partners in order to collect all the material, energy, and other type of information that we need for our evaluation. As you can see, this is the work activity for the LCA and the LCC because they are very connected, because the boundaries are quite the same and the data collection are really connected. After the data connection, we started with the data elaboration. So we organized the information on our Excel file, and then we model this process on the CIMAPRO software, sorry, that is a software for the LCA evaluation, in order to obtain the project results. Regarding the social LCA, the work was quite different because we started with the survey definition, also in this case working together with the project, the other project partners, so the technical partners, in order to better define and to better wrote this survey. So we developed the survey, and then we sent this survey to company and to several stakeholders in order to collect data and information. That we, after that, we elaborate this data in order to obtain, also in this case, the results. I will present very only one result for each evaluation. This is, for example, I forgot to put this not so important information. So this is a flow pack. There is very little word there. So the flow pack, the first one column is regarding the benchmark, and the second one for the preserve demonstrator. The results show, as probably is obvious for who works in this matter, higher value for the bio-based products respect the fossil-based products, and this is also a trend that we can find in literature. But because the bio-based industry is a very young industry at the moment, then there is also a high degree, as you saw in the previous presentation, there is a high degree of variability depending on the material, on the process, on the methodology that we can use for the product production. So all these variability can affect the results, also because sometimes we have to do some assumption in order to have the results. And so at the moment, it's not so easy to compare results for the bio-based products that we developed in the project with the fossil-based, where there are years and years of research and experimentation. So we have to continue our work in the future in order to have always a better definition of the process, and also with the industrialization of the process, we can have a lower a lower amount of energy, of materials, and for sure in the future these results will be better than now. For the LCC, we evaluate the direct cost and also the environmental costs. And as you can see, obviously, the market cost is very much lower respect to the hidden costs, because in the market cost there isn't the cost for the environment. So as you can see, for example, in the benchmark, the LCC, so the direct costs are very low, and and for the eco cost there are quite three oddio, centesimi, I don't remember, cents, 3 cents for each pack. That is not so convenient. For sure, for the preserved flow pack, the value are higher for the same argument that I said for the LCA, because they're a young industry, because of the process choices, but also it depends on the variability in prices that follow all the international trends, and also because at the moment the costs for bio-based products are not competitive with the fossil-based, because there are, as said, decades of research and also more interest in the international trade-off. For the social LCA, we saw that, for example, regarding the results of the answer of our survey, the level of the education can affect the type of answer, but in each type of level of education, the costs remain the main important aspect that people consider. People are really interested in the educational activities regarding this matter. So people are interested in knowing information regarding for example, the plastic packaging, the environmental consequence of the use of the packaging, and also for example, the environmental impact connected with the end of life of the products. So are all these matter that people are interested to know. Regarding the industry and the actor of the value chain, for sure the main obstacle are the production processes that, as you can see in this today, we are in the developing phase of these processes. At the moment, the cost that is higher respect the fossil-based, and also the European and also national regulation, because at the moment there are many rules that are developing. So industry are quite afraid at the moment because of this regulation. And regarding the consumers, we saw that usually they accept a higher, not so high, but price for the biobased and so the more sustainable packaging respect the classic one. So, Carla, the floor is yours. Green. Next.
Thank you, Matteo. Well, I'm Carla. I work at ITENE. So ITENE is a company dedicated to the packaging value chain. So we are located in Valencia, in Spain. So one of the tasks that we have was to analyze the circularity. So first, I would like to introduce you what means circularity, because there are some new faces here. So circular economy, it's too high for me. Circular economy is a model of production and consumption which involves sharing, reusing, recycling. Okay, so the existing materials, and we try to extend it in the cycle as long as it's possible. So in this way, the life cycle of the product is extended. So we try to reduce waste to a minimum, and we create further value. So we try to depart from the traditional linear model to a circular model. So we use the methodology commented by Ellen MacArthur Foundation. So at this moment, the current economy can be described as linear. So where virgin materials are taken from nature, and then they are disposed. So you can see here an image. This will be described perfectly. So we take, make, and dispose. So the opposite concept would be like the circular economy, where we make, use, and recycle. So it's based on 3 principles you can see here on the slide. So first one is design out waste and pollution. So focuses on eliminating waste and pollution, but this is very important at the design stage. The second one would be keep products and materials in use. So in this principle, try to emphasize the importance of maintaining the value of the product and material by designing for reuse, repair, manufacturing, and recycling. Again, we see that the importance of the design stage. And also the last one will be to regenerate natural systems. So here we try to return the valuable nutrients to the soil and avoiding the use of non-renewable resources. So this could be like composting or recycling, okay? Okay. So now we can talk about the aim of Preserve. So here the aim of Preserve in circularity was to determine how circular the value chain of the materials and the products developed within Preserve are. So for this task, we analyze the circularity of the benchmark, so the current packages that are on the market, and then we analyze the circularity of the demonstrators that were developed in Preserve. So how we have done this is with the material circularity indicator. So this indicator was developed by Ellen MacArthur Foundation again. So this indicator measures the extent to which the linear flow has been minimized and restorative flow maximized for the component materials. So it's essentially based on 3 product characteristics. So first, the mass of the virgin raw material, the mass of unrecoverable waste, and then the utility factor that accounts for the length and intensity of the product use. So this indicator goes from 0 to 1. So 0 will be like linear product, and 1 will be totally and fully circular product. So a linear product could be that a product that contains no virgin, that contains only virgin feedstock and then ends up in landfill. So this could be zero circularity. The result will be 0. So this is linear. And if the product contains no virgin feedstock and is completely collected for recycling or component reuse or for instance composting, then we'll have a fully circular product, which will be the result of 1. So I have here some results that we have obtained in Preserve. So here you see the benchmark, which is for the snack flow pack. So you have here an image. So the description will be of the structure will be polypropylene and metallized polypropylene. So for this one benchmark, the end of life, we made 2 hypotheses. So it could be energy recovery and landfill, or we could say that in a future could be recycled. So for this benchmark, the result will be, for the first hypothesis, 0, which means it's a totally linear product. And for the second, will be 0.44. And for the demonstrator, you have here the structure. So we incorporate the BioLDPE and also the whey protein, and then the wet adhesive. And in this case, the end of life would be recycling, and the indicator was improved, this indicator to 0.1. It's not totally circular, but we have a huge improvement in this indicator. And also, I have included here another structure. The demonstrator is not correct, so it's PHA film, paper, and PHA film. But we see, in this case, the improvement is not so high, but because in the benchmark, we also have cardboard. So this also improves, it has a high circularity in the results in the indicator. But for instance, the PE is energy recovery and landfill, so the end of life, and the cardboard is recycled. So we have an indicator that is 0.5, which is also for the benchmark is high, really. But in the demonstrator, with our structure, the PHA, we have 2 hypotheses. So it could be that the PHA is only for energy recovery and landfill, so it's 0.87. But if it's composted, could be the best option for us, would be 0.97. So it's mostly a fully circular product. So, the message that I would like for you to take home is the importance of redesigned packaging. So we all have been commenting this in our presentations. So this way we improve the end of life of the product, as well as redesign the feedstock origin. So we have seen that if we move to bio-LDPE instead of polypropylene, we see this improve in the circularity indicator. So again, design is a force for change. So we have to design for recycling, and design has the power to reshape our economy. And we have seen that the circular economy takes a different approach. So we try to eliminate waste and pollution, circulate products and materials, and regenerate nature. So this is all from my side. So I hope you like it. And I don't know if I think we end these first presentations. So I don't know. Thank you, everyone.
Okay, thank you to all the speakers for these very nice insights of the results of Preserve. I hope everyone have enjoyed it. I don't know if maybe there are some questions for any of the speakers in the room or in the online session.
Just before you mentioned some, I would call it like sustainability KPIs for packaging, right? So to what extent is actually the KPIs, LCA, or whatever you mentioned there, to what extent is it made by assumptions, and to what extent you can say it's really something exact? Or in other words, if you have two companies or two people like having these KPIs, wouldn't they come because they make totally different assumptions to totally different KPIs at the end? How do they look like? I was here.
Sì, ma non ho capito. Poi c'è una telecamera davanti. Qual è la domanda?
Excuse me, could you repeat the question, please?
Matteo.
Now I remember, it was you. You told something about like measuring or giving KPIs, key performance indicators, for sustainability of packaging, of material, right?
Yeah.
So you said something that you made assumptions. So my question is, how much is assumption and how much is really like, you can say it's an exact value for that goes in the equation? And if you have two different companies that do the same and have one of these KPIs, so I call them probably about sustainability KPIs. If you have two different people, two different companies doing this, wouldn't they come to different results because they make totally different assumptions then? And even interest-driven assumptions, perhaps.
No, but quite the total data are direct information from the companies. Where we have different companies that work on the same demonstrator, we obtain different results. So we try to model different processes, but sometimes there are some assumptions, for example, to upgrade some information that sometimes are at the, I don't know, experimental stage, in order to try to compare with industrial data. Not the same data sometimes are at the same level of come si può dire? Quella là. Yeah. Thank you.
Okay, so that means at the end it's not really comparable. Totally. You can't have this, you can have.
Excuse me?
Because the Zoom people don't hear us.
Yeah. We can, I think it makes it easier. So perhaps we can talk later then. I think it's, and also some other questions later on.
Thank you.
Stop all the...
Thank you very much. It's also related to the LCA. You are working with CIMAPRO. That means you developed your processes yourself based on the data collection you did in the different companies, or were you using different kind of databases like EcoInvent?
Yeah,
Sorry.
okay, for where we have the information from the partners, we modeled the process in CIMAPRO, but for sure then for other processes that derive from the literature, we use EcoInvent. I didn't put in the presentation, but we work like this. Also for the benchmark, was the same.
More questions?
There are quite some questions here in Zoom. Thank you for everyone who's online. If you need some time here at the room to think about any potential questions, I can read out loud the questions here in Zoom, and then we can continue. So we have here a question, a first question. It's about protein coating. So for the experts already, in which format protein coating is applied?
It's a wet coating, and you can also do it by cast film coating, for instance. So that's how we did it. But I have to be honest, I'm not sure if there also would be other possibilities, but that's how we did it and how it worked.
Thank you. There's another one. This is for Centexbel, for Willem. Who manufactured that used PHA? What type of PHA? PHB, PHBV?
We use different types of PHA for different demonstrators. So, for example, for the cup, we will use one type of PHA. For the coatings, we use another one. Mostly we use high crystallinity grades of PHA, like a PHB or a PHBV.
Thank you, Willem. I see here more questions. I'm just going to say very quickly something. It's not a question, but the slides will be shared. The agenda is in the Eventbrite page. The slides will be shared after that because there are some comments. Another question for Anna Südpack. Which PHA used in the production of 1,000 meters of casted pure PHA formulation?
So, as Willem said, we work with different types. We cannot share this. This is formulations, confidential information, but we do use some combinations with semi-crystalline PHA combined with amorphous types, but I cannot disclose exactly what we use.
Thank you, Anna. Let me see, there is another one. I see that Lola, our dear Lola from IMPLAS, is in the chat and has answered a question there. Hi, Lola. She's one of our project partners and is joining us online. Another question for Südpack I have here, Anna. How many extrusion cycles can these materials undergo?
Which material? PLA, PHA? What are we talking about here?
It's a different person, so I'm not sure. I don't think it's a follow-up question from the PHA. If this person is in the chat and could please maybe clarify what is meant?
I can try to do it generally. So it depends. For bio-based polyolefins, we are confident that it can overcome several cycles. Actually, we are trying to do this as well in our company to recheck how many cycles it could go through this material. For PLA, those are compostable material, which are normally more thermosensitive, and we have to be conservative here and say maybe less than a bio-based polyolefin, but chemically, from the point of view of chemical structure, the bio-based polyolefin are very similar to fossil-based, and we think we can be mindful here and say like it could be comparable with fossil-based, but it depends of the material exactly.
Thank you very much, Anna. We have, thank you in the chat, you're very active. In the meantime, if anyone here also wants to put a question, you can raise your hand and then we can also have questions here. Perfect. Let me get one more from Zoom and then I pass you the microphone, Mark. How many presented solutions has achieved commercialization? Anna?
So we have to be clear here, this is an innovation project. We are trying to bring this to the market, but some final optimization must be done. As we already commented, we are in one hand with end users, and they help us to realize what is missing, what we have to do to achieve the market. But still, this is an innovation project, and we have to work a little bit more on that.
Just a second, because there was a follow-up comment on for you, Anna, but this question about the materials, they meant upcycled materials for non-food packaging applications, just as previously. But
so generally, you mean again?
So you have answered the question. Thanks.
When we talk about circularity, and that's for you, Carla from ITENE. We try to keep the materials in as high quality as possible in cycles, right? And if you design new types of packaging, wouldn't you want to keep those materials in loop because you have a successful separation, recycling pilot plant? Have you been looking into reusing those different streams in reproducing packaging? and not already thinking about an upcycling, but a really recycling of the different streams after separation? And if not, what are the barriers to that?
But, well, we have included the recycled streams as well as the bio feedstock, but I'm not sure because in circularity, the formula, I included the end of the life. So if the product was recycled, we also take into account like the efficiency of the recycling. I think that answers your question, I guess. And also, if it comes to landfill or energy recovery, these waste streams are also included in the circularity formula.
Yes, thank you. But I mean, what I really mean by that is for the whole project of Preserve, have you been looking into furthering the life of like the recycled streams of your different packaging subcomponents to reuse them in packaging and not in upcycled second life for the same purpose?
Yes, we have included because some of the demonstrators have this. For instance, for D2, also some of the materials can be recycled into the. I don't remember the demonstrator, but yes, we have taken that into account.
Thank you.
Sorry, just to add to this, actually, there is a good question, and here I'm coming close to Estela, because actually the main barrier for the recycling of food packaging right now, one of the main barriers is policy and contamination. So that is also why the Preserve project is innovative, because we are trying to change the design of food packaging so that is also in bio-based packaging does not end its life in compost, that it's better than ending in landfill and incinerated, but also can be upcycled. So there you see the demonstrators. The bottom one is the one for secondary raw materials. So the idea is also to be aware that bioplastics and bio-based packaging can be reused many times, but the barrier right now from food packaging is contamination. So, and apart from contamination, right now the Commission is really working a lot on the policy for food packaging. And Estela, after in the innovation and the presentation of the innovation roadmap, we present some of the challenges. And so European Bioplastics is working also on trying to lobby in order to have policies that are really following the science advances and the research advances. So here, thank you, Estela, for being here, because I think also the collaboration between the different partners in this project has been really fundamental, because it represents the whole value chain for bio-based packaging and also the different opportunities that we have from research in bio-based plastics and packaging in going forward, because right now we are working a lot in end-of-life and compostability of bioplastic, but there is more. And at the European Bioplastic Conference, we saw that some people are starting to work on different end-of-life for bioplastics, but Preserve is really going forward and thinking that this project was written around 5 or 6 years ago, if I'm not wrong. So 5 or 6 years ago, a group of researchers that is right now in this room thought that bioplastic could have a different end of life instead of composting. I think is really innovative. So thank you so much again for being here and to so many bright minds together. And that's it, sorry. I hope I answered the question, Mark. Thank you.
She's Mara Menela. She's our exploitation and innovation manager at Preserve, for those who don't know her. Any more questions? I don't have anything in the chat here. My name is Estela Lopez Hermoso. I'm from European Bioplastics. I also didn't introduce myself. If you have any other questions, otherwise we're a bit ahead of time. Wonderful.